Hello everyone and welcome. In this video we're going to express the Euler-Mascheroni constant gamma as some integrals. Okay, let's get started. Now let's recall that gamma, the Euler-Mascheroni constant, is actually defined as the limit of h sub n minus natural log of n, where h sub n is the nth harmonic number. And it can also be defined as the limit of h sub n minus natural log of n plus 1. Okay, so remember these sequences, u sub n and a sub n. They're going to be useful later on. So we're going to start with the first representation of gamma as an integral using the sequence a sub n. So gamma is given as the limit of a sub n, and a sub n is simply the sum as k goes from 1 to n of 1 over k minus natural log of n plus 1. Now we want to look at natural log of n plus 1 as a telescoping sum. So we want to look at it as the sum as k goes from 1 to n of negative natural log of k plus 1 plus log of k. Okay. Now, this can be actually seen as some function which has been evaluated from k to k plus 1. And that function is simply x over k minus natural log of x. And this precisely is an integral. So we can write this as the integral from k to k plus 1 of 1 over floor of x minus 1 over x dx. Now, because we have a sum of integrals, and those on interval that actually touch at a single point, we can actually write this as a single integral from 1 to n plus 1 of 1 over floor of x minus 1 over x dx. Now, if we take the limit, we obtain an improper integral, so the integral from 1 to infinity of 1 over floor of x minus 1 over x dx. And this is a very simple representation of gamma as an integral. Now let's look at more complicated representations of gamma. So this time we're going to start with h sub n. Well, h sub n by definition is the sum as k goes from 1 to n of 1 over k. But we can actually rewrite 1 over k as x to the k by k evaluated from 0 to 1, and which in return can be written as an integral. Okay, so we can rewrite this as the integral from 0 to 1 of the sum as k goes from 1 to n of x to the k minus 1 dx. Okay, now we're going to take the sum because we are between 0 and 1. So if we take the sum is simply 1 minus x to the n by 1 minus x. Okay, now we're going to use the King's property to rewrite this integral so that we have x in the denominator. So we're basically going to replace 1 minus x with x. So we're going to get the integral from 0 to 1 of 1 minus x to the n by x dx. Okay, now we're going to perform a change of variable. We're going to set that x is equal to t over n. And that's going to give us the following integral. So now we have the integral from 0 to n of 1 minus t by n to the n divided by t dt. Then we're going to split our integral into two integrals, from 0 to 1 and then from 1 to n. The second integral can be split it even further by considering the difference that we have in our integrand. Okay, so now notice that we now have natural log of n because the integral from 1 to n of 1 over t is simply that. Okay, so now we can subtract natural log of n from both sides, and we know that h sub n minus natural log of n is simply u sub n. So we're going to get that u sub n is integral from 0 to 1 of 1 minus t by n to the n divided by t dt minus integral from 1 to n of 1 minus t by n to the n divided by t dt. So now we want to rewrite the last integral as an improper integral from 1 to infinity. In order to do that, we're simply going to multiply the integrand by a cutoff function, meaning the characteristic function of the interval from 1 to n. And we get the following. Okay, now we can take the limit. Now as we take the limit, we get the limit of u sub n, which is equal to that. Okay, now we can use the dominated convergence theorem. So the limits are going to move inside the integrals, and use the fact that the limit of u sub n is actually equal to gamma. So we're going to get the following. Okay, now we're going to use the fact that the limit of 1 plus z by n to the n as n tends to infinity is equal to exponential of z. This is true for all complex numbers z. In particular, it's going to be true on the set of real numbers. So we're going to just replace our z by negative t. So if we do that, and the cutoff function is going to be the characteristic function. So the limit of the cutoff function is going to be the function that is identically 1 from 1 to infinity. So we're going to get that gamma is equal to the integral from 0 to 1 of 1 minus e to the negative t by t dt minus integral from 1 to infinity of e to the negative t by t dt. So this is the first representation of gamma by integrals. As you can see, we have two different integrals here. Okay, now we want to take this even further by integrating by parts. So let's integrate by parts. Okay, so we're going to get the following. Now, the first and third term are 0. You can actually check that. So if they are 0, this means that gamma is actually equal to negative integral from 0 to 1 of e to the negative t natural log of t dt minus integral from 1 to infinity of e to the negative t natural log of t dt. And we can combine these two integrals into a single one. Okay, so we have this beautiful integral. So gamma is equal to negative integral from 0 to infinity of e to the negative t times natural log of t dt. Okay. Now, we're going to perform a change of variable here. We're going to say that t or x is equal to e to the negative t. That's going to give us another representation. Now, if we say that x is equal to e to the negative t, then we're going to get as new limits 0 and 1. Or if you want 1 and 0. And therefore, we're going to get the following representation. And I think this is a good place to stop. Thank you for watching and see you next time. Bye.